Okay, here we go. Start. We are still in 3.1. Well, we actually just started it last time. Let's recall some things first. One of the problems on your test, how do you define the derivative? Limit as h approaches 0 up. Right, so it's the difference quotient as the denominator goes to 0. So that definition, then you can just plug in a function into this, and you find what's called the derivative of the function as long as this limit exists. So that's something you should always remember. Last time I introduced one of the shortcuts for this guy when your function looks a certain way. It was x to the n. And what was that?
Nx to the power of n minus 1.
Right, so basically if your function looks like this and you plug it into that definition, the answer will always be this. So now you just have a shortcut. Now you know that every time something looks like this, that's going to be the derivative. We did a few examples. So common example, something like x squared, which is 2x. Right, you bring the 2 down, subtract 1 from the power. We did some other examples. How do you do something like that? I don't remember if I gave you that.
Not the cube.
Hmm?
I don't think we did the cube.
Okay, well, how would you do that one? So you first you rewrite it before taking the derivative, right? So the minus 1/3 is how you deal with that guy. And minus 1/3 x. Negative 4 over 3, right? Subtract 1. To subtract 1 from a fraction, just put the denominator over itself. So it's minus 1 over 3, minus 3 over 3, which gives you minus 4 over 3, and that is the derivative. What does that mean? How does this relate to that function? What's the relationship between these two? What does this function tell me about that function? The slope of the function, right? So if I'm on the graph of this guy and I'm at a certain x value, I want to find what is the slope at this point? What is the tangent, the slope of the tangent line at this point? Or how fast is the function changing at this point? I just plug in that x value into this function. That's what the derivative is about. Note. The derivative is a limit, right? That's the definition of the derivative. So it shares, I want to tell you about. Shares all the properties, some other properties. So let's talk about some properties of derivatives, some ways we can think of more general situations. For example, there was one property of a limit that says we can factor constants outside the limit. In the same way, if we have a constant times a function, we can actually factor out that constant and multiply by the derivative of the function. So that's one property of a derivative because it's a property of a limit. You can factor constants outside. So for example, if I didn't just have like x squared, if I asked you to differentiate 3x squared, what would be the answer? Well, you can literally factor the 3 out because it's a constant and just differentiate x squared. And so the answer here would be 6x. Or in other words, if you have a constant times a function and you want to find the derivative, just leave the constant alone, it'll just stay. And then you differentiate the function part and multiply it. Because constants can factor out. Also, another thing, a property of limits, is the limit of a sum is the sum of the limits, which means if I take the derivative of a sum, probably shouldn't say all here. There's a subtle, we'll talk about a subtle difference. Many. Because there's a subtle difference here. Okay, so, but just like limits, the derivative of sum is the sum of the derivatives. So I can just differentiate each part. Differentiate that function, plus or minus, find the derivative of that function, add them together. Example. So if I actually find the derivative of x squared plus radical x, that's just the same as the derivative x squared plus the derivative of radical x. Which is equal to derivative of x squared, just 2x plus derivative of radical x. 1/2 x to the minus a half. Right? So if I have a sum or a sum of terms or a subtraction of terms, I can just differentiate each part, and that's my overall derivative. And by the way, you don't have to write this from now on. If you jump from here to here, that's completely fine. Just know if you have a plus or minus sign separating terms, you can just apply your rules to each term and just keep the sum or the subtraction. Some other important rules. I mentioned this a long time ago when I introduced the exponential function e to the x. So now I'm just going to remind you. The derivative of e to the x is itself e to the x. So for example, if I ask you to find the derivative of 3 over radical x is 2 plus e to the x. What is that equal to? Negative 3 over 2. How are you getting that?
Change the value of x to the negative 1/2.
All right, first you'd rewrite this because I don't have a rule that has a radical in it, so I'd rewrite it to get rid of the radical. So this is just 3x to the minus 1/2 plus 2 plus e to the x. And so now I apply the power rule here. The 3 is just a constant, so it just stays. The minus 1/2 comes down, multiplies that 3, I get minus 3 over 2. What does the power become? Also minus 3 over 2. It's minus 1 over 2 minus 2 over 2, giving me minus 3 over 2. Derivative of 2? 0, it's a constant. And the derivative of e to the x is itself. So this is just something we know now. Memorize. Derivative of e to the x is itself. Another important rule is the derivative of the logarithm, ln. Turns out that this is 1 over x. You didn't know that before, now you know. And this is just something that we know now. I won't prove it for you. The proof is a little bit subtle, but that's what it is. An example. ij. Here it is.
3x to the minus half.
No. 3 over 2x to the minus 1 half. Right, this guy is x to the 1 half. The half power comes down, which gives me 3 over 2. Subtract 1 from the power. It's itself. Derivative of e to the x is e to the x, and a constant factor just stays, hangs out. Minus 3 over x. Right? So technically this is 3 times 1 over x when I take the derivative, and so I just multiply it. So that would be the answer. Not so bad. Another rule. This is generalizing the exponential derivative, where a greater than 0 is a constant. For example, if I'm differentiating something like 2 raised to the x power, right? In this case, my a is number 2. And so this is just 2 to the x times ln of 2 would be the answer. And again, this is just something that we know now. If a is a number e, it still works. Right, so it's e to the x is just a special case. If this derivative would be e to the x ln of e, but ln of e is 1. So you still get e to the x. Right, so this is a much more general formula, and it still works if your constant is the number e. Find the derivative. Answer. Minus 3 times what? What happens? I can't hear you guys. Times 1 half. Right, that's a constant raised to the x power. So it's the same function times ln of the constant. So here's a part where form actually matters, right? It matters whether the base is a constant or the base is an x. Notice that here, you would use the power rule applies. Right? Right here, you can't use the power rule. So now we're in the era where paying attention to form really does matter, right? So if you ever see this and you write something like x times 2dx minus 1, it's so wrong, super wrong. I'm just going to give you 0 for everything and just not think about it. I'm just going to stop reading at that point, right? Pay attention to the rules. You have to be in a certain situation to apply a certain rule, right? So it matters whether the base is an x and the power is a constant, as opposed to the power of the base is a constant and the power is the x. It makes a lot of difference, right? So the derivative of this guy, if you want to differentiate, that gives you 2x, where this guy would give you 2x ln 2, right? They're very different functions. They behave very differently. So just because you see something to a power, don't think, oh, power rule. It's not always a power rule. It depends greatly on the form and the kind of function you're using. This power rule works with polynomials. This is an exponential, two very different kind of functions. So, let's do a word call. Word problems, okay. A very standard kind of problem you'll see both in this class and when you do something like physics. The diver is giving up on life and he decides to jump off, right? Even though he had his whole life ahead of him. Right. His height above the water is given by this function. S of t is equal to minus 16t squared plus 16t plus 32. By the end of the class, you'll figure out how to even derive that formula even if you don't know it in the beginning. But for now, let's say I gave you the formula that describes his position, and now let's answer some questions. A. When will the diver hit the water? B. What function describes his velocity? Time t. C. What is his velocity after 1 second? I didn't tell you what the units were. S is in feet, T is in seconds. Should have mentioned that earlier, but that's it. So this describes his height, where S tells you the number of feet he is above the water, and T is the time in seconds. D. What is his impact velocity? Right? That means when he hits the water, how fast is he moving at that point? function describes his acceleration. That's the rate of change of his velocity. When is it moving up and down? G. And is his velocity 0? When is the instant where he's not moving? Okay. Very standard kind of problem. A problem like this is guaranteed to come up on the next test. I won't ask you G parts, but you can expect 3 or 4 parts. So maybe up to part C or D, and I'll ask you questions similar to these and some other variations. And you'll also see problems like this within the first week when you take a physics class. You'll see problems like this. It's called free fall. And they'll just give you equations like this to use if you're doing physics 203. But I'm going to even show you how to derive these functions by the end of the class. We need integration to derive it. Okay. So that's the actual problem. So let's solve it. Ideas, part A. Right, he hits the water when the height equals 0. This function gives me his position above the water, right? So this tells me whatever height he is at above the water. So if I want to find when he actually hits the water, his height above the water is 0. So I'm just going to set S of t equal to 0. Need height S equals 0. This means that function minus 16t squared plus 16t plus 32 equals 0. How do I solve that? Factor out what? 16. So let's factor out a minus 16 to make it a little nicer. This is t squared minus t minus 2 equals 0. How do I continue? Huh? What does this become here? You try to FOIL, see if that can work with t and t. The only way you get a 2 is a 2 and a 1. What are the signs? So minus 2 and a plus 1. You multiply these two, you get minus 2. You add those two, you get minus 1. And so we have 2 options. Our t is either 2 or our t is minus 1. Now we're nowhere near quantum physics yet, so negative time doesn't make sense for us. So t equals minus 1 is rejected. Because we don't have negative time doesn't make sense for us. So after t equals 2 seconds, he hits the water. Right? So in this situation, if this is the function that describes his position, he will actually hit the water 2 seconds after jumping off the platform. Didn't really use calculus there, that's just a matter of algebra. Just solve that quadratic equation. B, how can we describe his velocity? Derivative. Remember, we know that velocity is the rate of change of position. V of t is equal to s prime of t, right? That's the relationship between position and velocity. So this means that if I want to find his velocity function, I can just find the derivative of his position function, which is the function over here. So what's the derivative of that? Minus 32t plus 16. And that's the function that describes his velocity, as in how fast is he moving and in what direction. C, what's his velocity after 1 second? Just plug it in. We want V of 1. V of 1 is going to be equal to, just plug in 1 for t here, minus 32 times 1 plus 16 equals minus 16. And in this class, I don't care about the units, but it would be feet per second. FYI, the minus sign means, what does it mean? It means direction. What direction does it mean? Is going down. Right, so the way this equation was set up, it assumes that moving up is the positive direction for velocity and moving down is the negative direction. So he's going down. So after 1 second, he's already on his way down. D, what's his impact velocity when he hits the water? How fast is he going?
Set velocity to 0.
No? How do you know how do you know velocity is 0? In part D, we don't know the velocity. They ask you what the velocity is. Why would I need the second derivative? What?
So you find the velocity at 2 seconds?
Why? Right. Before we figure it out, he hits the water after 2 seconds. So if I want to know what's his velocity when he hits the water, it's his velocity at 2 seconds. So basically I'm going to plug in 2 into the velocity function, which is this guy. Which is going to be, what's that, minus 64 plus 16. About minus 48. So yeah, it's no joke. He really wanted to off himself. You know how fast that is? You're traveling 48 feet every second. That's super fast. I don't think he made it. I hope he got 10 points for the dive. Right, so that's how fast he's moving when the moment he hits the water, he's moving at that rate, which is actually pretty fast. I don't think he survived. E asks, what function describes his acceleration? Because I know here it's water after 2 seconds, want velocity there. Acceleration? That's, now we have the second derivative. The acceleration is the second derivative of position, or equivalently is the first derivative of velocity. So this means this is just the derivative with respect to t of minus 32t plus 16, which is just minus 32. So his acceleration is actually a constant. Again, in this class, I don't particularly care about the units, but for your education, it's feet per second squared. That's the rate of change of speed. And that number actually means something. What's that number? Gravity. This is the acceleration due to gravity. So if something is just falling, that's how fast gravity is going to change its speed. It will increase its speed by 32 feet per second. So it's minus 32 per second squared, or in meters per second squared, it's minus 9.81. Which is something you're going to have memorized at some point. By the end of this class, you'll need to remember that. It's not going to be a fact anyone's going to give you after a while. They're going to expect you to know that. So that's the acceleration due to gravity. Meaning neglecting air resistance, if you drop something, if it's not moving after 1 second, it will be moving at 32 feet per second. After 2 seconds, it will be moving at 64 feet per second, and so on and so forth. Every second, gravity is going to speed it up by 32 meters per second. F, when is he going up or down? How do we figure that out? When what?
When speed is positive or negative.
Right. Remember, up means velocity is positive. Down means velocity is negative. How do I find where it's positive and negative? How do I do that? Set it equal to 0. So if you want to figure out where something's positive or negative, first you set it equal to 0, and then you test on either side of all those guys to figure out what value it is. So I set v of t equal to 0. This means that minus 32t plus 16 is equal to 0. This means t is equal to a half. Right? So now what we do is on the timeline, set t equals into a half. Obviously, for us, time less than 0 doesn't make any sense, so we're stopping there. And so I can just plug in a number over here, so like a quarter, right, or 0.25. And if I plug in a quarter here, I actually get a positive or a negative number. Positive. I get a positive number, which means increasing, means he's moving up. If I plug in a number over here, like 1, I get a negative number, which means he's actually moving down. This means he's moving up for t in this interval, 0 to 1/2 seconds. So the first half a second, he dives off the platform, he actually goes up for a little while, and then he goes down. After a half second till he hits the water at 2 seconds, he's moving down. Right, so he travels up for half a second and falls for 1.5 seconds. When is the velocity 0? Oh, we actually solved that, I think. So there are a couple ways you can think about that as well. He's moved when the velocity is 0. Well, let me actually emphasize that. Because the idea is here, he's moving up for half a second, and when you go up to start moving down, you have to like stop for an instant and then start changing direction, right? Which gives you another thing that I could ask on a test. I could ask something like h. What is the max height that he attains, right? At what point is he the highest above the water? And I could just say for max height, v equals 0, right? Because that's what's going to happen. He's going to stop for an instant and then start going down. Right? That's one way you can talk about the max height. Another way you can think about it is you want to find the maximum point of the position function, which from your quiz you'll remember that means when the derivative is 0 and the derivative changes sign on either side. Where on the left it's positive, on the right it's negative. That will give you a max point. So this happens when t equals 2. So a half. So what's his maximum height? I know velocity equals 0 at time equals a half, so max height would be what? Max height can't be 0. We know at one point it was 32 feet above the water, so it's definitely not 0. It has to be at least 32. Well, I'm being asked about height, so what should I be looking at? The original function. That was the function that told me about height. I know the velocity equals 0 at time equals a half, so what's the max height? Or how do I find it? That's the approach. You plug in a half into the original function. So max height would just be s evaluated at half, which is going to be equal to minus 16 times 1/2 squared plus 16 times a half plus 32. It's minus 16 over 4 plus 16 over 2 plus 32. 16 over 4 is 4 plus 8 plus 32. So it's 36 feet. So that's the highest he attains, right? So he jumps off the platform, which is 32 feet high. He rises to 36 feet. He attains that height after a half a second, and then he falls for 1.5 seconds, 36 feet. And by the time he makes it there, he's traveling at minus 48 feet per second. So his day did not end well, but we got a good example out of it, so I think it's worth it. Okay. Any questions about that process? Very typical word problem. It's definitely coming back here, and you'll see those in your physics class as well. The first class, maybe. Okay, so that actually ends 3.1. For the moment, we're skipping 3.2. I'll come back to that at the end because it has some applications into it. Right now, we're just going to actually jump to 3.3. We're going to talk about the product rule and quotient. Let's start with the product rule. It's called a product rule because this is used to differentiate products. Why do you need a product rule? If I have two functions multiplying each other, can I just take the derivative of each one and then just stick them together? The answer is actually no. some point I'll want to be able to differentiate the product of two functions. And we'll see why in a few examples later. B is because so for example, if I wanted to differentiate 5x, it's not true that I can differentiate this and get 0, and then differentiate that and get 1, and the answer would be 0. That's obviously incorrect. I know the answer is 5, right? Whereas if I differentiate something like x squared, I know the answer should be 2x. But if I think of this as two things multiplying, x times x, I differentiate this one, I get 1, differentiate that one, I get 1, it will give me the answer 1, which I also know is not correct, right? So when two things are multiplying, how do I actually differentiate them to make sense of it, right? Well, you'll need the product rule, right? Because it just doesn't work to differentiate each part, which students do all the time. Don't do that, it doesn't work. So now let's figure out what does work, right? If I have two things multiplying, how do I differentiate them? We already know how to deal with a constant case, that's just the first property, but what if it's another function? What if it's something like x times e to the x, or x times ln x, or e to the x times ln x, something multiplying. So let's actually figure it out. So let's say I want to take the derivative of one function times some other function. How are we going to figure that out, Jhevon? Well, definition. To find derivative, you need to take that limit. So what is the limit going to look like? It's the limit of the function evaluated at x plus h. So this is f of x plus h, g of x plus h, minus the function evaluated at x, f of x times g of x, all over h. So now I'm going to try to figure out what would that actually give me. So we're going to do a little trick like we did when we're completing the square from algebra. We're going to add 0 in a convenient way to simplify things. So I'm going to add and subtract a term. And this is going to be the term. I'm going to subtract f of x times g of x plus h. And I'm going to add f of x times g of x plus h. Just because I feel like it. No, not because I feel like it. But why'd you do that, Jhevon? Well, let's see. Notice here, I can split the fraction up into these two parts. In this two terms, g of x plus h is a common term, so I can factor that out. And I'd be left with plus, in this case, f of x is a common term, so I can factor that out, and I'd be left with and now I can take the limit using the limit properties, right? I know the limit of a product is the product of limits, and what's this limit as h goes to 0? That's right, it's f prime by the definition that we have memorized right now. Right? Limit as h approaches 0, this guy's f prime. As h approaches 0, this guy just gives me g of x because h is 0. Plus, this is just f of x, there's no h in it, so it stays. What's the limit of this guy as h approaches 0? G prime, that's the derivative by definition. Hence, we have a rule. If I have two functions multiplying, that's how I find their derivative. rule says, and this was a bonus in your quiz, the derivative of two functions multiplying is the derivative of the first times the second plus the first times the derivative of the second. F prime g plus f times g prime. That is called the product rule. You don't have to know the proof for it, but this you have to memorize. I'm going to ask you that on a test or a quiz, and you're going to have to know it anyway to do the problems I'm telling you. So that is called the product rule, and it's how we differentiate the product of two functions. Of course, let's do some easy examples, the one I mentioned before. So I wouldn't use the product rule here, but I could. This is just, it's going to be the derivative of 5 times x plus 5 times the derivative of x. So I know derivative of 5 is 0, so that's just 0. Plus derivative of x is 1, so I get 5 times 1, and the answer is 5, which actually works out. Again, I wouldn't use the product rule to do this, but I could. If I think of this as x times x, then do the product rule. The derivative of x is 1, leave that guy. Then leave the first guy, derivative of that x is also 1. And again, I get 2x. Okay, seems to work with the guys we know. Let's do something more complicated. That function, x times ln x. Answer.
Plus x 1 over.
Of course, that can simplify. X cancels x. So the answer is ln x plus 1. So the idea is you're faced with this. You have to see it as two functions multiplying each other. This I can call an f, that I can call a g. And the answer is going to be f prime times g plus f times g prime. By the product rule. And by the way, the order doesn't matter here, right? Because multiplication, it doesn't matter what order you do it in. In addition, it doesn't matter what order you do it in. But I recommend memorizing it in this order because of a rule that I'm going to tell you about later, where the order actually matters. Differentiate that. Well, that's your derivative. Don't give yourself a brain hammer, rewrite it first. First thing you do is rewrite that, and then derivative of this. No. How do you do this? Power rule. Minus 1/2 x to the minus 3/2, right? So that's the power rule. Don't forget the power rule. Look at this guy, you can look at this as there are two functions multiplying. I have a 2x times an e to the x. So this I think we have an f and a g. Or I could just leave the 2 and think of it as x times e to the x. You'll get the same thing anyway. So you get 2 times e to the x, because that is your f prime, that's your g,
2x.
plus
2x. E to the x.
2x, that's your f, you just leave it alone, times the g prime, the derivative of e to the x is just e to the x. And so that's going to be your answer. We're going to figure out the derivative of 1 over a function, a non-zero function. You'll see why later. So for now, we're just going to do this random thing. So if I need to figure out a form for something that I don't know, I use the definition. So let's use limit as h approaches 0 of 1 over g of x plus h minus 1 over g of x all over h. Simplified. How do I get that? How do I figure that out? That's limit as h approaches 0 of 1. It's a complex fraction. What do you do with complex fractions? Multiply and divide by the LCD, right? Form recognition. What's the LCD here?
Gx plus h and g of x.
G of x plus h times g of x. You multiply and divide by that. Right? Don't let the fact that it looks scary fool you. It's a complex fraction. We deal with all complex fractions exactly the same way all the time. Right? So now, when I multiply out this times this, that just gives me g of x. This times this gives me g of x plus h over h times g of x times g of x plus h. Now what I'm going to do is I'm going to factor something out. I'm going to factor out minus 1 over g of x times g of x plus h. Why would you do that, Jhevon? Let me see. What would I be left over with? G of x plus h minus g of x over h. And that guy, we actually know what that is, right? What's that? That's the derivative, that's g prime of x. And if I take the limit as h approaches 0 of this guy, I just plug in h equals 0 here, and I have 1 over g of x squared. So it turns out the derivative of something that looks like this is that guy. Why do we care? Here's another task. I want to find out the derivative of a division. I'm not just going to assume it's the division of derivatives because that didn't work last time with the product, so I don't think it will work with fractions. But here's how we're going to do it. I'm actually going to rewrite this. Right? So now what I have is I have two functions being multiplied together, which means I can use the product rule. So the product rule says, what do? I differentiate this, leave that one alone, plus leave this one alone, and differentiate this. Well, what is the derivative of this? It's that. So this is minus 1 over g squared times g prime. So now I have f prime over g minus f times g prime over g squared. Let's say I wanted to write that as one fraction. What would I do?
LCD again?
Huh? What did you say? I want to combine the fractions. How would I do that?
LCD again?
Okay, and what is that?
G times G squared.
Okay, so how do I fix it?
You multiply f prime by G squared.
Multiply by g over g, right, to make the common denominator.
Oh yeah,
Algebra. Right, so this becomes f prime times g minus f times g prime all over g squared. This gives another very important formula. It is called the quotient rule. The rule says the derivative of one function divided by another function is actually going to be the derivative of the first times the second minus first times derivative of the second over the bottom squared. Okay? So it's the bottom times derivative of the top minus the top times derivative of the bottom over the bottom squared. This is called the quotient rule. We use this to differentiate quotients, or divisions of functions. And this is something we know now. You don't need to know how I derived it, but you need to know this, right? If you want to differentiate one function divided by another function, that's the rule. Example. Differentiate x divided by e to the x. So I have that function, and for some reason I want to find the slope. What would I get? Huh? 1 times e to the x. No. E to the x then squared, which is not e to the x squared. What is that actually? Laws of exponents says you can multiply these. It's actually e to the 2x, right? So you look at this, what you see is one function, which is an f, divided by another function, which is a g. And so what you do is you do f prime times g minus f times g prime. Derivative of x is 1, derivative, and then you have e to the x. Then you leave the x, you find the derivative of e to the x, which is just again e to the x. In this case, we can actually simplify a little bit. E to the x is a common term in the numerator. I can factor that out. I'd be left with 1 minus x divided by e to the x squared. This will cancel one of those. And so my final answer is 1 minus x over e to the x. So if I have that function, that gives me the slope. One thing worth mentioning is, notice that I derived the quotient rule using the product rule. You can actually do that in practice, right? So sometimes if you really don't like the quotient rule for some reason, I don't know, you could actually bring this up, write it as e to the minus x, and then just use the product rule. And then you'd simplify and you'll actually get the same answer. I don't necessarily think it's worth it most of the time, but you know, if you have some psychological aversion to the quotient rule, it makes you feel unhappy for some reason, you can always use the product rule. But this is the quotient rule, very important, must be memorized. I will be testing you on it. And you will need it because you're going to be differentiating things like that all the time. How do you differentiate that? I'd use the power rule, personally. Right like that, it's minus 2x to the minus 3. Which leads us to a very important recommendation. Don't use quotient rule if numerator or denominator is a constant. It's just a lot of effort that you just don't need to go through. And I've seen students try to go through it and make mistakes because it just makes things more complicated than it has to be. Right? So just because you see a division doesn't mean, oh, quotient rule. Sometimes you can actually rewrite it and use the power rule or some other easier rule. Right? Similarly, if I ask you to differentiate x cubed over 2, again, I would not use the quotient rule. I'll just look at that as 1/2 times x cubed. Just use the power rule. So if your constant is in the denominator, you just factor it off. It just means there's a fraction multiplying your function. Good, how about that? Over 4x all squared. Way too complicated. Again, I wouldn't use a quotient rule here. There's an easier way.
Every term on 4x.
Divide 4x into each term. This is basically asking for the derivative of 3 over 4x minus 1/2 plus 3 over 4 times x to the minus 1. it's just the power rule. Derivative of this is just 3 over 4. Derivative of that constant is 0. Derivative of that is minus 3 over 4 x to the minus 2. So if denominator is if there's a single term in the denominator, one term, then before just jumping into the quotient rule, I try to see if that term can divide into everyone very nicely. So we're learning some cool formulas, but with great power comes great responsibility. Right? Sometimes you need to know when not to use a rule just as well as knowing when to use it. Right? Why? Because if you make things more complicated than they have to be, that gives you room for errors. You make mistakes when there's just no point in making them. Right? So if your numerator or denominator is a constant, or if your denominator has a single term in it, odds are you can simplify, and you should try to do that and apply some simpler rule. Okay. But there are times when it doesn't really simplify, and that's when you want to use the quotient. But in general, you're going to want to keep things as simple as possible, and so don't use a more sophisticated rule when a much simpler rule would work. Time, let's just throw some examples here. Example, differentiate x plus 1 divided by x plus 2. The other example, I'm going to show you something. Well, let's just get through these two and then we'll call it a night. Okay. So you see here, you see a division of two functions. You don't have a single term in the denominator, so dividing into each term is not an option. Sure, we could bring things up and do the product rule, but why bother? So this is f, and that's our g. So I know the answer is going to be f prime times g minus f times g prime all over g squared. So it's going to be the bottom times derivative of the top, right? Derivative of the numerator is minus the top times derivative of the bottom over the bottom squared. And run out of space. So this just is, what do we get here? X plus 2. Right, because the negative sign distributes over x plus 2 squared. X kills x. 2 minus 1 is just 1, so I have this. So that function gives me the slope of that function. So you know this guy is your f, that guy is your g. So you have the bottom times the derivative of the top. Derivative of ln x is 1 minus the top times derivative of the bottom over bottom squared, which is e to the x squared or e to the 2x. Now we can try to simplify. How? Oh, doesn't ln x kill e to the x? Can I turn this into x? No, I can't. Why not? Because that ln of this guy and e to the x is being multiplied separately, right? Remember, it's when the e to the x is inside the ln, they cancel. Right? Pay attention to the rules, close attention to the rules. Right? This guy's outside your ln and it's multiplying, so the log rule does not apply here. But e to the x is a common term, I can factor it out. And so I can have that. Right. What is a complex fraction? It's kind of nasty to write it like that, but you could. It's the same as this. Just multiply by x over x and you get that. And that's the quotient rule. We ended section 3.3. So we're done there. I will see you guys on Wednesday, and we will continue. I'll talk about the chain rule next time.